Welcome, everyone. Thanks for the patience. Sorting out a few technical issues. Welcome to the Snapps Bootcamp. We're really excited to have you here, the entire O1 Labs team and Mina Foundation. My name is Jason. I'm a product manager at O1 Labs for Snapps, and excited to kick this off. So let's get started with overview of the agenda for what we'll be doing this weekend. First, we're going to start with an intro session. Congrats, you made it, and everyone through the technical difficulties. So this bootcamp is going to be structured into two main sessions, an intro session and a wrap-up session, and then we'll have 3 office hours in between. At these office hours, a pair of O1 Labs devs will be available. So if you get stuck on the project that you're working on, which will be introduced later, you'll have the chance to ask them about it. And we also have a channel on Discord that's called Snapps-Developers, where you can get help from other participants in the program as well. So we have the 3 office hours in between. And then importantly, Sunday, we have the project submission deadline. So the project that you're working on or will work on during this program, we'd like everyone to submit it by 7 a.m. Pacific on Sunday. So that gives us a little bit of time to review and pull out a couple to have people share during the wrap-up session so we can all kind of learn from each other. For today, we're going to start off talking about the Snapps Builders program, then a brief overview of Mina and some use cases for Snapps. I'm going to talk about the architecture of Snapps, how it's designed. Then we're going to talk about SnarkyJS, a brief recap of sort of the basics of that library. And then we'll have a couple examples. We'll have a sudoku example and a TicTacToe example. And then we'll have Brandon introduce the projects that you'll have the chance to work on. And then we'll talk about some next steps and then have an open Q&A at the end. So I'm going to pass it over to Bijan, who's the head of product at O1 Labs.
Thank you, Jason. Hi, everyone. I'm Bijan, head of product at O1 Labs. Very, very excited to be here. I know that this is something that we've been looking forward to for a long time. So let's jump right in and get started. So the Snapps Builders program is a program that is very important to us, especially at the Mina ecosystem, because it's really being built for the developers that are interested in building on Mina. Give you guys a bit of a context about it. What it is that it's a program that's going to enable the developers that are interested in building on Mina to be the first batch of developers that are going to launch their snaps on Mina in close collaboration with O1 Labs and Mina Foundation. We'll be providing them with support on a one-on-one basis. We'll provide them with some resources from our engineering team to make sure that they're able to get answers to any questions that they may have. And we'll also use this as an opportunity for ourselves to develop a product roadmap and set of additional features that are really driven by the needs of the developer community. And it's a really good way for those of you that are interested in contributing to the Mina ecosystem, because you'll have direct impact on the roadmap of SnarkyJS and Mina as a whole. This is a program that we're keeping it actually to limited spots, and the main reason for that is we want to make sure that Mina and O1 Labs are able to actually provide proper support for teams or individuals that are interested in participating and building with the Snapps Builders program. There will be an application process that you can actually follow here. This is where you actually would be submitting your projects by the end of the bootcamp. The deadline is Sunday the 12th and 7 a.m. We'll be reviewing them and sharing the results with you guys after that. Right now, our anticipation is that the program will take about 3 months. Whether it's going to be a couple weeks more or less, that's something that will be determined as we start working through the program. But some of the project details, such as project plan and what the exact outcome of each project is going to be for each individual or each team that gets into the program, will be determined in collaboration with O1 Labs and that entity or that team or that individual. There will also be a grant that will be awarded to each participant. It's $10,000 dollars in Mina tokens, and that will be a great way, hopefully, to provide additional support for the interested individuals and teams. Now, in terms of selection criteria, what we're looking for are projects that are going to be really looking at leveraging the unique privacy aspects of Mina and ZK Snarks. And we know that we're really entering a new paradigm of privacy applications that could have never existed up until now. So we're very interested in working with projects that are really thinking about leveraging some of those unique capabilities of privacy that are provided by Mina, and hopefully by the end of the bootcamp, you all have a much better idea of what those capabilities are. We would also like to see that the participants have an end goal in mind, and it doesn't mean that you have to have like some sort of a commercial product. It could be just like a simple end-to-end user experience. It could be a simple game. It could even be a prototype that demonstrates what the Mina's SnarkyJS capabilities are and what ZK Snarks are all about. So there's a lot of room, I would say, for the applicants to select a particular goal, but the main kind of objective to keep in mind is to have like some sort of an outcome that they're working towards by the end of the project. And we'll also review their quality of work and quality of code. Of course, for a variety of reasons, we want to make sure that it's something that if they're interested in building down the road, building further on down the road, it's possible. So ideally, the codes are readable, efficient, and basically meet other requirements for a good quality of work. So that's it from our program. Very excited to see what you guys will come up with and what you'll submit. And I'm going to pass it to Evan here.
Thanks, Bijan. Let me just pull up my screen. And let's see if I can, thank you. Okay, cool. Great, okay, thank you, everyone. Thanks for being here, it's very exciting. So I just want to give a quick overview of Mina, just a reminder what the project's about and how Snapps fit into it and everything. Mina is a very lightweight chain. This allows it to be very decentralized, and it does this by embedding zero-knowledge proofs very deep into the way the protocol works, which also gives us the ability for developers on it to build things like Snapps that we're doing today. So why this matters is crypto is facing some challenges due to not having some of these features. For one, blockchains by default are very heavy. It's very expensive and difficult for users to access blockchains without going through intermediaries, because you have to download the history of the chain in order to be able to know that you're looking at the correct state of it. Zero-knowledge proofs let us get around this in a very elegant way, where the zero-knowledge proof gives us a proof of the entire history of the chain up to the current state, and just downloading that gives you the whole protocol. It also lets you decentralize at scale. So as Mina increases its throughput, we'll be able to do that without having any risk of that increasing decentralization, because you'll still be able to check this very small proof, even as Mina is doing higher throughputs, has applications that are effectively acting as whole rollups. It'll let us do some very cool scaling things. And lastly, you have these challenges around privacy and verifiability with crypto today. Because you don't usually have things like zero-knowledge proofs available, you have to put all your data on chain, you have to put everything in public, and you can't really have privacy around sensitive data, and you can't put large computations on chain. These are some issues you have. So zero-knowledge proofs, as I've said, kind of solve this in a very elegant way. You can have these very small proofs that let you verify the entire history of the chain. You can also, this is also due to the way Mina's consensus is designed. You can have it set up such that there's no fixed cap on the number of validators or proof of stake. You can have as many people as you want participating, only limited by the likelihood that you actually win a block. So you can have very high numbers of people running block production, which we have pretty good numbers on Mina today. I think I'll share some of those later in this presentation. Users can also share proofs of their data with these zero-knowledge proofs, and so that they can be able to build with things like privacy, build with verifying very large amounts of data and very large computations off-chain, but putting those things on-chain in very kind of native ways to the L1. So that's the Snapps stuff we'll talk about today. So between this, we aim to build something that can be really empowering to users and can really put users in the driver's seat of cryptocurrency through this being able to have a very decentralized chain that gives these features such as verification and privacy and whatnot. So some stats since mainnet launch. The network has been working stable for over 8 months now, which is awesome. It's a long time for the network to be running, at least for us having just doing the test nets for so long and stuff. So it's really cool. There's currently more than 75,000 active Mina accounts on chain. At times, there's been over 1,000 connected nodes with the network running well. So that's very cool. The Mina mainnet saw very spikes in traffic when there's various things such as listings on exchanges and stuff, and the network is doing well for that. And we also have over 1,000 core community contributors and over 200,000 members participating in the community. So it's awesome to see the things starting to take off on the community side as well. So I'm going to give a really brief overview of Snapps. Presumably you've been to things like the workshop or you know about these already, or you'll learn a lot more on the talk, but briefly, what these are is decentralized Snark-powered applications. And there's two kind of key product features we think are really cool here. One is this, we're building things out with this technology called secure oracles to make it possible to verify information on HTTPS websites with pretty good guarantees and put that information on chain, either proof of the actual information itself, a computation on the information, or something that can include even privacy over that information. And also generally, both for this feature and just in general, you can build things that include privacy over user data when you're building things with the Snap. So here's some basic overview of what's going on and some use cases that plug into the existing crypto landscape. You'll see a lot more examples today of ways of using Snapps in actual applications, but a few here are, if you're building something with DeFi, for example, it would be awesome to be able to start pulling in information from the real world to kind of bootstrap that ecosystem, but you can't really do it today because it would involve pulling sensitive information on chain that you don't really want to. You don't want to put like my bank account information or your credit score and stuff on chain. But with Snapps and zero knowledge proofs and privacy, you can start thinking of ways to do that in ways that preserve user privacy while still allowing the interoperability of a public chain and the decentralization and censorship resistance of that. So that's one cool application. Another is building things such as verifiable NFTs. So we could have, for example, using the same technology, proving that I own a particular Twitter account and I own the tweets, and thereby building an NFT marketplace for tweets that is fully decentralized and users prove something about their identity and interact with it. And lastly, there's some very cool possibilities around just scalable compute in general, putting very large computations on chain. You should be able to with Snapps. You produce a proof on your computer, it takes a little longer, but then when you put it on chain, you can do it without the associated gas costs of doing that with Ethereum. And the primitives that come to mind for me are like sorting a very, very large list or just working through a very large data set or dealing with problems with things like machine learning. But there's probably lots of these that can be started to apply once you have zero knowledge proofs. This also leads to cool things like trustless bridging, where you can start having things like we're doing with Ethereum, where Mina is fully verified on the Ethereum chain. So just a quick kind of timeline of where things have been so far. So we selected JavaScript, TypeScript for the language. It's mostly implemented now, which is why we're able to have this bootcamp. And right now we're in the process of testing and actually, kind of sharing this out with the workshop and bootcamp that's going on. There will be a public testnet to start doing this stuff out soon, and then it will be deployed on mainnet. There will also be grant programs to come as well, including the ones that Jen mentioned earlier, but also others will be coming as well. So that's it for what I have to share on Mina and Snapps. Thanks for listening.
Great, thanks, Evan. Let me start my screen share. All right, so I want to talk briefly about how the architecture of Snapps, so kind of how they work from a high level. As most people know, Mina is kind of unique, or is very unique as a blockchain, because most other blockchains, they grow in size. They accumulate as new blocks are mined. For instance, Bitcoin is 378 gigabytes, and Ethereum is over 1.1 terabytes in size. whereas Mina remains a fixed 22 kilobytes in size. So we call this a succinct blockchain. Using recursive ZK snarks, we can compress the blockchain into a single ZK snark. So you still get that full node security, but with a much, much lighter weight size. A very large amount of research over decades and multiple teams has advanced ZK snarks. And recently, our cryptography team at O1 Labs created a ZK snark we call Kimchi, which is setupless, efficient, and extensible. It's based on Planck 15. With the Mina blockchain based on ZK snarks, we're also able to envision a smart contracting platform in a different way. So to look at Ethereum uses on-chain computation. Smart contracts execute on-chain, and users send a transaction specifying one of the methods on that smart contract along with data arguments. Every node across the Ethereum network executes the same instructions. It was amazing when it came out, but it's woefully inefficient. Mina Snapps use a different model. Users execute one or more methods of the smart contract locally and privately on their computer, generating a zero-knowledge proof. They then send this transaction containing the zero-knowledge proof and a description of associated state updates that are needed by the chain to the chain. The Mina network will then verify that this proof is correct for that particular Snap account. And if it is, the state is allowed to be updated. And if it's not, the transaction is rejected. Clients down the line can verify the correct state of the Snap account just by verifying proofs sent to the Snap account. There's no need to execute the full program and the full history like Ethereum would in order to confirm it. The program is only executed off-chain on the local machine before it's sent to the Mina network. This gives us a few advantages. We get scalability through the succinctness of the blockchain. We don't have that ever-growing size. And user privacy can be maintained using zero-knowledge proofs because the smart contracts are running on the client side in the user's web browser. So data can be optionally private or public, depending on what the Snap developer prefers. It also allows for unlimited off-chain execution. So unlimited in the sense that as a Snap developer, your main limitation is time. So how long will this application take to run and generate the zero-knowledge proof? But you don't have to pay on-chain gas fees for your execution like you would on other blockchains like Ethereum. So how does this work? A snap, as we call it, to define the terminology, we use the word snap to represent both the user interface and a smart contract within it. So most of the content of this bootcamp is going to be focused on the smart contract aspect of things. So the smart contract is what's written with SnarkyJS. A SnarkyJS smart contract, when the developer builds it, it compiles into a couple different artifacts. One is the prover function, which runs locally and generates the zero-knowledge proof. So for instance, when your user goes to visit a website, so say you were to visit the equivalent of Uniswap, but on Mina, the prover function would take any data that the user provides, and it would generate a zero-knowledge proof from this. Additionally, a verification key is created. The verification key is stored on-chain, and it is what allows Mina to verify the correct execution of the smart contract that ran off-chain. To deploy a smart contract, the developer sends this verification key to the chain. So a Mina account and a Snap account are really the same thing, except the Snap account also contains a verification key. And the verification key, of course, means that any transactions sent to that Snap account have to pass the verification key. And that ensures that the smart contract logic, as intended by that Snap account, has run successfully. And this just illustrates it running successfully. And if the proof is invalid, of course, the transaction is rejected by the Mina blockchain. And that keeps the state of the Snap account correct. And then lastly, to describe how a smart contract method works, and then after this, we're going to jump into SnarkyJS. Each method of a snap can accept multiple different inputs and then generates output. So you could have method arguments, which is going to be data provided, for instance, by the user in a user interface. You may also have smart contract states, so state associated with that particular Snap account. And then you may have other values from the Mina network, such as, say, the block height at that moment. And then it updates, or it outputs a list of updates to the smart contract state and other updates that the smart contract would cause. And now we're going to jump into SnarkyJS, which is how you write the smart contract, or what you write it with. Isaac?
Hey, sorry, I was on mute, just switching over. Can you hear me okay?
Yep, sounds good.
Sweet. So let's see. All right, can you guys see that?
Yeah, I can see it.
All right. I'm not sure how to get my, there, great, okay. Thank you, Regina. Okay, so this is just gonna be a bit of a recap from yesterday. If you weren't able to make it to the workshop yet, or sorry, not yesterday, but Tuesday. So if you weren't able to make it to the workshop on Tuesday, you're in luck. And if you did go, then, well, I promise it will be even more fun the second time. So, all right, so SnarkyJS is, as has kind of been mentioned, a TypeScript framework for writing snaps. It uses just existing open technologies. It runs in the browser and on the server using Node.js. And because it's written in TypeScript, it means you can use any existing like TypeScript libraries or tools. Just to call one thing out in particular, the VS Code support is really, really good. So there's really good autocomplete and refactoring and like doc comments on hover and all that kind of stuff. So we recommend using VS Code for developing with SnarkyJS. I'm just going to go through and kind of break down. This is like a crash course. So this is just going to be like 10 minutes, like super fast. Like here are all the basics of stuff in SnarkyJS that's not just TypeScript. So I'm not going to be explaining like all the specifics of TypeScript. There's obviously a lot of great resources online for learning about TypeScript if you're not already familiar. But I'm just going to be kind of highlighting the parts of SnarkyJS that are different from TypeScript, or normal programming in TypeScript, I should say. So field elements. Okay, so field elements are the basic unit of data in all ZK programming, and you can inside of a single field element, you can store almost up to 256 bits. You can think of it kind of like uint256 in Solidity, and just to kind of expand on it being the basic unit of data in ZK programming, it's a bit like how bytes are the basic unit of data in traditional programming. This is represented by the field type in SnarkyJS. So there's a type called field. There are operations that you can perform on field elements. So if you're just doing normal TypeScript programming, just working with numbers, you would write like sum equals 1 plus 3. In SnarkyJS, you need to kind of wrap it with this field element type, and you'd write it like this. So new field 1 dot add new field 3, or you can even just simplify it to just saying dot add 3. So so just to kind of sum up on that, there's a whole bunch of operations that can be performed on field elements, obviously not just addition. You can multiply them, divide them, like arithmetic stuff. You can compare them, you can convert them into bits, blah, blah, blah. So they're kind of this basic sort of numeric type. But there's a lot of other built-in types as well. So in the standard library, we have field elements, as mentioned. We have uint64s, uint32s. There's also like assigned integer, which isn't mentioned here, public key, private key signature. So that's a really useful building block to have in a lot of applications. Types representing optional data, Booleans, group elements, which is useful for various cryptographic protocols, scalar, which is like, for performing scalar multiplications on group elements. And these all have a lot of built-in functionality on them. Cool. And I'll just while I'm here, I'll just mention there's also inbuilt functionality for working with Merkle trees and also for computing Poseidon hashes. So if you ever need to hash something, there's functionality for that. I'll just mention a bit about implementing kind of like business logic or like game logic or anything like that in SnarkyJS. The main thing to call out is this will involve a lot of usage of the bool class. So that's how you represent booleans in SnarkyJS. All of the kind of usual Boolean methods are available. So like, you can do and, or, negation, pretty straightforward. The one kind of hitch is that you can't use a bool in an if statement. So instead, there is a kind of inbuilt ternary operator that takes a Boolean and two values and it chooses, either the first value or the second value based on whether the bool is false or true, or true or false. So I'm just going to call out also just like, this is just TypeScript stuff, but kind of just good to call out. Functions work as you'd expect in TypeScript. For example, here's a function that takes a field element, adds one to it and doubles it. Pretty straightforward, just do x.add1.mul2. And you can also, just like in JavaScript or in TypeScript, you can define variables. So here we define x plus 1, just x.add1, and then we return x plus 1.mul2. So that would be like another way of defining the same function. Oh, sorry, the title for this slide is slightly off, but the content is as intended. So in SnarkyJS, as I mentioned, we can define normal TypeScript functions, and we can also use for loops. So it's just a normal TypeScript or JavaScript for loop. Looks like that. For let I equals 0, I less than 10 plus plus I. You can do whatever you want. So just I'll pause on that for a second and just kind of mention like all the normal TypeScript stuff. It's there. I'm also just going to break down really quickly for those of you who weren't there yesterday how smart contracts look. I know Jason kind of went over it at a high level, but I just wanted to show you how it looks in code. So every smart contract extends the smart contract class. So if let's say we want to define a simple smart contract, hello world, you would extend this smart contract class. The next thing that's part of a smart contract is the state values that it uses. So this is on-chain state held in that Snap account that Jason was mentioning. So for example, this first line or second line here declares that this smart contract has a single state variable called x, and which has type field. Then you define a constructor, which basically defines how the snap is going to get deployed on chain. And then you can define a sequence of methods. Those methods are basically all the ways that people can interact with the contract. So if you want to interact with the contract, you basically send a transaction saying, hey, I performed this one method, and here's the proof that I computed it correctly, and here's the result. And if you want to kind of dive deeper into this, we can provide, I think it should be available now, a link to our talk from Tuesday, which obviously goes over all of this in a lot more detail if you weren't able to make it, and has exercises and stuff like that too. So it's a really good way to kind of get started if you missed the talk on Tuesday. And yeah, with that, I'll hand it over to Brandon, I believe, or Gregor. I'm not sure, or is it David? I'm not sure. Sorry.
Hi, I'm Gregor. I recently joined O1 Labs as a JavaScript developer. And today I want to show you an example of a little game implemented with SnarkyJS. Okay. So this game is Sudoku. And probably everyone of you knows how Sudoku works, but I'll briefly explain it. So we have a board of 9 times 9 numbers. Some of them are not filled out. And the task is to fill out every little square so that the numbers 1 to 9 appear in every row. Every number appears only once, and in every column, and in every square. So for example, in in the upper left one square, we'd still need the numbers 1, 4, 6, 7, and 8. And I want to walk you through a simple Sudoku snap. So on a high level, the idea is that we have a smart contract that has some sort of reference to a Sudoku, and any user can submit solutions to the Sudoku. So submitting a solution is a method on this smart contract. And whenever the solution is correct, so users in reality, users submit proofs that they have a solution, and these get verified. And if a solution is verified as correct, then the smart contract updates its state to solved, or solved is true. So this is all there is to it. It's quite simple, but it also means that the snap state provides a proof that someone solved the Sudoku without showing the solution. So we are demonstrating zero knowledge here. Okay, so I'm gonna share a different screen now, and I actually built this out with a simple web UI, and I'm gonna share that now. Here. Okay, so this is the UI. As you see, and so later I'll walk you through the code, but now I just want to show you how it works so you have a better idea what the code is doing. So first we can generate a Sudoku, and here we can have a slider that can adjust the difficulty. If we pull it higher, then more fields get filled out. So that's going to be an easy Sudoku. And here we can have hard Sudokus. And so if we then click deploy, it will take a while. And this Sudoku is now on the blockchain, basically, in the snap state. The snap state is shown here. And you see that there's a Sudoku hash. And a Boolean is solved. So the hash is just actually a field element, but I turned it into a hexadecimal number. And now we could fill in some numbers here. And then we could try to submit the solution, but so the feedback is not great here, but the solution, of course, is solved stays false because that wasn't the solution. And maybe to demonstrate an actual solution, I'll create a really easy Sudoku so that I'm able to solve it here. Okay, so here we need 4, and here we will need 9. I'll try that. Okay, now this solve is true, as you see, so that worked. So basically now the snap state is a proof that I solved this Sudoku. And because it has a Sudoku hash, it has a hash of the Sudoku, everyone with the Sudoku can verify that it's the right one. It's the same one. Okay. So I'll show you the code now. I'll share a different screen. We'll go to VS Code now. Okay. Oh, sorry. That was the. Sorry, I shared the wrong window. Here it is. Okay, that's the right one. So I have created a little project here. As you see, it's quite small. It only has basically 4 source files. And it's actually currently running the server and serving the UI that I showed you. So that's this little server here. And it's a React app. Here's the app. But I'll focus on this sudoku snap file. Where the actual smart contract stuff goes on. Okay, so I start with one thing. At the top level, I do await is ready here. That's a little quirk of SnarkyJS, because a lot of stuff has to be loaded so that our complicated functionality is ready, and that takes a while. So for instance, it involves compiling some WebAssembly. And that's why usually before we do anything, we have to wait is ready. Okay. The first thing we have to think about is the data structures. So our Sudoku will have to be a matrix of field elements, 9 by 9. And for this, we have this, we're defining a custom type here. It extends circuit value, and it will have props. And we have this matrix prop decorator that enables you to have matrices as prop. We also have array prop and normal prop. And it looks like this. This Sudoku gets passed a matrix of numbers. That's normal JavaScript numbers. And it just turns them into field elements. So that just maps the whole number array into an array of field elements and stores it in the value. And you see that this Sudoku also has a hash method that can hash the Sudoku. That just takes this array of arrays, flattens it into one array, and applies the Poseidon hash function. Okay, so next I'm going to talk how to actually use this custom type within a smart contract. So this smart contract, as you see, it has a field called Sudoku on it, but that's not a state, and that's because the Sudoku is actually too big to fit in the state, so we can't store the Sudoku as state on the Snap account. As I showed you before, instead we have a Sudoku hash. That's just a field, and a Boolean that says whether the Sudoku is solved. So we initialize the Sudoku hash by calling this Sudoku hash state.init, and similarly we initialize is solved as false. And the balance add in place you probably have already seen in the workshop, so I'm not going to talk too much about that. But I would just, before I get into the call logic here, I want to just show how these functions are called. So I'm scrolling down. So this is the usual setup that you may have seen already. I'm creating an instance of a local blockchain, so everything that happens in the browser window I showed is just locally in memory. And we also have some test accounts here. And then we have this deploy function. And this is a function that is exposed to the UI, to the React UI. So this is what is called by the UI, and also this one. So this is the main API basically that we provide here. And the deploy function basically just okay, it looks as if it's already deploying. That's just robustness. And if not, it starts deploying. It creates a random new private key. It creates a public key from the private key. And then it creates a transaction that deploys the snap. And that basically just calls this constructor. And constructor, the deploy function gets a sudoku. A sudoku is a matrix of 9x9 matrix that has some values not filled out, and a value that's missing is indicated by 0. So that contains numbers 0, 0, or 1 to 9. And then we instantiate a new sudoku and instantiate the sudoku snap. We send our transaction and are finished. That's what happened when I showed you, when I clicked on the deploy button before. Okay, and now we're really in the interesting territory. Now we're imagining we're a different user who created a solution, and he calls submit solution now. That's also creating a transaction, and this transaction calls the smart contract method submit solution. And this solution now is also expected to be 9x9 matrix, which doesn't have any zeros. And we instantiate with the same constructor as before. Okay, let's look at submit solution. This is now the complicated part. So we should first think about what we have to check. We want to check that this solution. So we have notice we have the sudoku that was passed in the constructor, and we want to check that this solution is now a solution to this sudoku. So the first thing we check is that the solution is a valid, finished, solved sudoku. That means we have to check the rows, the columns, and the squares, that they all contain the numbers 1 to 9. So I defined a little helper function here. This is basically the core thing that takes an array of 9 field elements. This could be a row, for instance. And it asserts that this array contains all the numbers 1 to 9 exactly once. How it does this is I created this 1 to 9 thing here, which are the field elements from 1 to 9. And for each of those, for each number from 1 to 9, okay, I check all the values in my array of, for instance, in my row, and look whether they equal this number from 1 to 9. And I want that at least one of them equals that number. So I reduce all these equals. These are bools. I look if some of them fulfills this. So that means this line basically checks that k is contained in this array. So we do this for every number from 1 to 9. So we see then that every number from 1 to 9 is contained in this array because we end these conditions all together. So each of those is true. So all of the numbers from 1 to 9 is contained in the array, and it's important that we access the array here only we don't map over the array here, but over the indices. That's important because the array could also be something bigger. If someone wanted to cheat, could have more elements, and then it would be easier for it to have the numbers 1 to 9. But we only check the first 9 indices of the array. So that actually makes it a sudoku. And at the end, reduce bool end gives us a boolean here, because bool end gives us another boolean, and then we call assert equals true. That says that it is true. So, and now we apply this function to the different parts of the Sudoku. We first loop through all the rows. You see, again, this is normal TypeScript, and we just call this function. Assert has 1 to 9. So the row has all the numbers 1 to 9. And in my representation here, a row is just, the rows are the first indices and the columns are the second ones. So one member of this solution is a row, and the columns we get here, that's just mapping the rows to their jth index that will give us a column, and we assert that this column has the numbers 1 to 9. And then we check all the 3x3 squares, and that's it. So I'm not gonna explain now how I'm creating a square, but yeah, it's straightforward. So after all these checks, we know that solution is a valid solution. But we also have to check that it is a solution to our Sudoku. So for each cell of the Sudoku, they have to either be equal, or it's one of the cells where the Sudoku is empty. This is what we check here. So we look at the Sudoku cells and the solution cells, and we check that either the cell equals 0, the original Sudoku is empty, or the cell equals the solution at this value point. So the solution is actually equal to the Sudoku at all the non-empty fields. And after that, we all again have to assert that this is true. So this is one gotcha, that we always have to assert that our booleans are true and not just form them or create them. Okay, now we know that this Sudoku that we got passed is an actual so the solution that we got passed solves the Sudoku that we got passed, but we're not finished. And this was actually something that I missed when I first implemented it. I thought actually I was finished here, so that was my original program. But colleague Brandon explained to me that I also so the point is that the Sudoku is not actually on the blockchain. Just the hash is on the blockchain. So that's why I then introduced this hash. So we take this Sudoku and hash it, and we check that it is actually equal to the Sudoku hash. And the Sudoku hash we get from the blockchain. That's this.sudoku hash.get. So we're finished here. We solved the Sudoku, we solved the right Sudoku, and the Sudoku was actually the one that was originally deployed. So now we can, after all these checks have passed, we set this is solved to true. And that's it. Okay, maybe now that I explained how this works, do I still have time left? So I think I'm basically out of time.
Yeah, actually, if you would like to take a few more minutes, yeah, this was great.
Okay, cool. So maybe I talk a bit about how to integrate this into the UI, because that's not so. It's not so hard, but it's also not so trivial. So we'll change files here. And I need to talk about a third function that probably you're all gonna need, or anything similar, a similar function, that's getting the snap state. So our web application has to fetch the snap state to show the user what has happened on Mina. So the way this works is we get the snap account. Okay, I'll make this a bit bigger. And .snap.appState gives us the snap state. And this is async because this actually fetches the state. Not in this example because this is a mocked Mina version, but in the production version it will be that way. And then you notice, you can see that we access the snap state now with indexing, because this is not the raw field element, so to speak. Before our isSolved was a bool, but now it's just a field element. It's just a field. So we convert it back to bool. So snap state 0 has the sudoku hash, and snap state 1 has the isSolved boolean. And I want to show you why that is, because if we go to the top, you see that we define sudoku hash first and isSolved second, and that's it. That's why, and this has the size of one field element, and the bool is also the size of one field element. That's why this is index 0 and this index 1. Okay. So we're basically deserializing this into nice JavaScript values, so that this is a string that looks like a hash, and this is a boolean. Okay, that's the interface our smart contract file provides. Deploy, submit solution, and get snap state. And now we want to briefly look at the UI code. Very briefly, I guess. Okay. So we have a little React app here, and this has two views. The first view is generate Sudoku, and the second is where you can solve the Sudoku. And we'll in the generate Sudoku view, we have this little plumbing to always generate a Sudoku whenever the slider is moved. So this gets this ease parameter. That's what the slider was changing. And whenever ease changes, we have this effect running that generates a new Sudoku. Okay, so the Sudoku value is whatever has been created last. And then we have this deploy function, which it sets a loading state. And this is a very important point that I just wanted to make. In the deploy function, I actually import the Sudoku snap code. This is this code. So this was generated with TypeScript up here. And I use dynamic import here. And the reason for that is that SnarkyJS takes about 3 or 4 seconds to load. So it takes quite a while to load. And we don't want to happen that in the beginning, because if it happens in the beginning, the page will just freeze and show nothing for 4 seconds. And that's why I moved this import here into another function where the user expects some kind of loading to happen. So we just mix these two slow operations together. So that's not too bad for the user, I think. And probably most bundlers will understand this and will create separate chunk. So my bundler created sudoku snap chunks here and sudoku. So yeah, app.js. So this will be a separate file and will be loaded later, basically. And then we call the deploy method and are finished. Yeah, and it works similar with the other. So I'm not going into any details how I actually created the sudokus. Most of the rest is just standard, but you can look at the Git repository later. And in the solve sudoku view, we have a submit function, and that's simple. That just calls the submit solution, and that's it. Oh, and after it submits the solution, it calls pull snap state, and that will actually, I have created a little hook here that will give me a new snap state, and the new snap state is then shown here below. So this is also not normal React stuff. Okay, so I guess I'm finished. And to recap briefly, or maybe I'll just I just stop. Bye.
Oh, feel free to recap, and I'll just wait.
Okay. Sorry. Okay, all of that has been said. So what this demonstrates is we use zero knowledge because the solution was private. It was not stored anywhere on the blockchain, and still we had a proof that there was a solution. And you saw how we can check a fairly complicated condition just by using our built-in functionality, making assertions. And it's really important that you think deeply about what you have to assert to make a proof. And we have seen an integration in the web UI. And you can look at this link to see the full project. Okay, and that's it. So, David, it's your turn.
All right. Thanks, Gregor. Let me try to share my slides. Okay, can you see my slides?
Yep, that's good.
Yes. All right. Up. Cool. Yeah, so I'm David from the crypto team, and I'm going to talk about a TicTacToe example. TicTacToe is interesting because there's a state and it's interactive, so you can see how different players will interact with the snap. And if you don't know what a TicTacToe is, it's going to be complicated. I'm just assuming everybody knows. But all right. So a snap will look like this. There'll be a deploy method, so the constructor, and this will work for 2 players. And these 2 players will have public keys. And so you deploy, it's a very simple example. So you deploy a snap for these 2 players and they play the game. And once they're done, they can't play anymore. And actually, it's not very secure if they try to redeploy another one. It's not really going to work for some reasons. So very simple example. And then there'll be only one method, a play method that takes coordinates X and Y to know exactly where you want to play on the board, and some authentication stuff just to make sure you're the right player. So public key and signature. But I'll talk more about that later. And so as I talked about the hello world of smart contract, you just import SnarkyJS, you extend the smart contract class. So I'm not going to go too much into the details here. And what's really important here is to figure out what's the state of the snap. And here we want to represent the board. So TicTacToe is a 3x3 matrix. But as we said previously, if you want to represent each tile of the TicTacToe with a field element, you're going to be running into some problems because you only have 8 field elements in a snap. So you could use option states if you want. But it's going to be kind of annoying. So for a simple example like that, So here we can actually just represent the board in one field element. We just have to write some encoding and decoding or serialization, deserialization logic, and then it'll be fine. So that's going to be kind of the trickiest part of this presentation is how do we encode the board into a single field element, and how do we decode it? And then we need a few more variables in the states of the snap. We need a next player variable just to know which player has to play next. Here we use a Boolean, which is a type built on top of a field, but it's easier to use. And false means player 1, true means player 2. Pretty basic. And then we need one more variable called game done. And this will be false throughout the game. And once someone wins, we set it to true. Like that, the snap knows that the game is ending, and nobody can keep playing on the same snap. And then we're getting also the 2 players public keys. These are not in the state of the snap on chain. They're not variables that you can mutate. I said that you can only deploy your contract for 2 players, and that's it. So we actually hard-code them in the contract. So that's why they're not decorated with the states decorator. Okay, one last thing. So there's a constructor. I'm not going to talk about that. You've seen that in the previous talk. So it just initializes the state to 0 or false or these kind of things, and it sets the 2 players public keys that we want to our 2 players, and then it does some weird stuff with an address and initial balance. This is subject to change, but this is not super important for what we're doing here. So yeah, I don't know if I can take questions because I know we're a lot of people. So I'm just going to let you ask questions on chat, and maybe someone else can answer, or maybe I'll take some time at the end to answer questions. But hopefully that's clear. It's just a simple state. You could have come up with something else, but this is what I came up with. All right. So we're going to implement the play function. So that's the most important thing here in this presentation. So now is the time to start focusing, I guess. And this thing takes X and Y coordinates. So imagine the X-axis, Y-axis in this diagram that I put there. And 1 and X equals 1, Y equals 1 is like the middle tile. And it takes a public key and a signature. And you're gonna see why. Also, it's decorated with this method decorator. That's how you write a method. And it's asynchronous for some reason. And at a high level, this is what the logic is going to look like. We're going to check if the game is already finished first. And if it's finished, we abort. We're going to do some authentication stuff just to make sure that the player playing is actually a player, one of the 2 players. We're going to make sure that it's their turn to play. So if player 1 tries to play and it's player 2's turn, we're going to tell them no. And then it's going to get a bit trickier. We're going to deserialize the board, which is a field element, into our 3x3 matrix. And once we have our 3x3 matrix, we're going to update it with the move we want to play. And then we're going to check if that move just made us 1, and if so, we will update the snap. Okay, so I'll recap that as I go along through the steps, but that's the high level. So first one, checking that the game is not already finished, you need to check the game done variable in the snap states. So to get the snap states, you do this.gamedone.get, use this get function. This is actually a call to the blockchain. So it's asynchronous, so that's why you have to await it, and that's why the function is async. If you don't really know, TypeScript or Rust or like these languages that have async keywords, it doesn't really matter at the end. You just have to remember to write await there. And once you got this variable from the state of the snap, you just assert that it's equal to false. And asserting things is the typical way of writing snaps. You just, you're writing your program and you're just asserting things when you don't want your program to take a path. And you don't care if it crashes or anything like that. It's a very simple way of writing programs. You're not a service that needs to handle errors or anything like that. Okay, so hopefully that makes sense, that first step is relatively easy. The authentication, we start by checking that the public key that was passed as argument, this pub key. I don't know if you can see my cursor, but basically we check that the pub key is equals to player 1, or that it's equals to player 2. The keys are hard-coded in the contract. And all of these are Booleans, but not TypeScript Booleans, but SnarkyJS bools, so that we can convert them into a circuit. So you have to use these built-in functions. And then at the end, we just check that this is equal to true. So that should be pretty basic logic programming. The second thing we want to do is to verify a signature over the coordinates. So if you've ever used a signature verification library, it's pretty straightforward. To verify a signature, you need the signature, you need the public key of the player, so the one we just passed, and you need the message that was signed. And the message that was signed here is just an array of the coordinates. And remember, the coordinates x and y are field elements. These things should return true. We make sure that it returns true with this assert equals. Again, authentication stuff. Yeah, just authentication stuff. Right. So now we need to make sure that it's our turn. And to do that, we first recreate this variable that represents the player as a Boolean. So if our public key is equals to the player 1 public key, which is hard-coded in the contract, we return false, because false represents the player 1. Otherwise, we return true. I could have written that in a different way, but I just wanted to showcase that circuit if here. And once we know who that public key is associated to, we can check that it's equal to what the snap is expecting. So we get this next player variable from the state with the same technique. We use this get keyword, and then we just assert that it's equal to player. So hopefully that makes sense as well. If we're player 1, this variable player here will be false, and so we need to make sure that what's on the snap state is false as well. And then we need to set the stage for the next player. So we set the snap state to false if we're the player true, or true if we're the player false. So that's how you change the state of a snap. You just use the set function. So pretty straightforward. You just use get if you want to read the snap state, or you just use set if you want to set it. All right. Okay, so hopefully that will make sense. If something didn't make sense, I'll share a link to a tutorial that we wrote at the end, so you can actually follow this in a written form. So don't worry if you disconnect at any point in time, but this will be helpful to understand the actual code. So now is the tricky part. So now it's time to really focus. If you're not focusing already, we're going to try and deserialize the board. So first we get the board from the snap state. Remember, it's a field element, a single field element. So as Isaac said earlier, it's a pretty big number that can contain a lot of information. What we're going to do is we're going to convert it to bits, because it's easier to think about bits than large numbers. And we only need 9 bits here. So we're just going to get the first 9 bits. So basically, we're transforming our TicTacToe, which has 9 tiles, into these nine bits from the field element. That's what we're going to do. Now, if that makes sense, can anybody see why this is not going to work? Can anybody see the problem with this? And there's probably too many people, so that's rhetorical questions. Pretty much the problem with that is that a tile in the TicTacToe game has 3 states: the empty states, the player 1 has played their state, and the player 2 has played their state. And in a bit, you can only store 2 states. So that's not going to work for us. So naive solution is to actually use two lists. One that tells us if a tile is empty or not. So 1 here means that this tile is not empty. 0 means that the tile is empty. And then we use another list, which tells us what player actually played in that tile. So 1 is the cross here, player 2, and 0 is player 1. 1 is actually the circle, and 0 is player 1. So be a bit careful here because, again, we can only have 2 states. So 0 actually also represents the empty state. So that's why we need the 2 lists. So if that makes sense, what follows is not too hard to understand, I believe. Instead of deserializing the board that we got from the snap states, we deserialize it. Instead of deserializing it into 9 bits, we actually deserialize it into 9 times 2 bits. I believe that's 18. And then we slice it into, well, we split that into 2 different arrays. The one that represents if it's empty or not, and the one that represents if it's what player actually played there. And because we're going to recreate our state of a 3x3 matrix, we do a double for loop, pretty standard. And inside the for loop, we're going to just get the not empty variable and the player variable, so false or true, depending on what player played. We're going to push that in our state, in our 3x3 matrix. So that's probably one of the hardest slide to parse, but there's no real magic here. It just reorders variable into a state, a 2-dimensional array, so that it's easier to play with it. And here, so every tile here is basically going to be an array of 2 elements, something that tells you if it's empty or someone has played there, and something that tells you who played there. And that's actually a bit complicated to think about, so I'm going to use a type instead called optional. That's in the library, the standard library of SnarkyJS as well. And just think of optional as, instead of having an array and saying, like, I want the first element in that array or the second element, this optional has a variable called isSum that tells me that it's pretty much the not empty. That tells me if there's someone that played there or not. And also a variable called value that tells me who played there. Oops. Who played there. So every tile in my TicTacToe now, in my 3-dimensional, my 3x3 matrix is going to be an optional that tells me this, giving me this information. Okay, so hopefully that makes sense. Or am I on time? Okay, I think I'm good. So, okay, now we're going to update the board. Or maybe I can leave that slide on for a few seconds. I don't know if that's helpful. Yeah, so just understand this is the deserialization, and know we have our 3x3 matrix of optionals. Okay, so let's update the board. The first thing we need to do to update the board is to check if X and Y are valid coordinates. Maybe I can give you some time to parse that. But we're just playing with Booleans here. Just making sure that X equals 0, 1, or 2. So nothing tricky, hopefully. And same for Y. Y should at least be equal 0, 1, or 2. And then what we want to do is to update our board, so our deserialized board, at the index X and Y, the coordinates. We want to set that optional. I put it back here. We want to set isSum to true because someone has played there. We are playing there. And we want to set the value to our player token. So false if we're player 1, or true if we're player 2. The problem is that we cannot do that. We cannot do dynamic indexing in Snapps or in zero knowledge smart contracts in general. And here I say dynamic indexing because X and Y are arguments of the method. So what we have to do is actually go through the entire states and only update what we need to update. So that's something to think about when you're writing Snapps. You cannot do this. So we'll do a double for loops to go through every element of our states. And we'll create this toUpdate variable that is true if X equals I and Y equals J. So if we're at the point in our loop, which is representing the tile that we want to update, then toUpdate will be true. And then we need to make sure that we can actually play there. So what we do is that if it's the tile that we want to update, if toUpdate is true, we'll get the board at these coordinates, and we'll get the isSum value. And we'll make sure that it's false. We're making sure that there's nothing there. Nobody has played there. If we're not updating this tile, then we just return false here, which is always false, so we don't care. We're kind of ignoring other tiles. And finally, basically what we do is that we copy every cell of our board. So board ij is equals to board ij. We just copy it unless we want to update it. So if we want to update it, we don't copy the board blindly. We actually create a new optional set to true, meaning that someone has played there. Who has played there? Player. So that's the variable that we created that represents us as a player. So false or true. And that's pretty much how you update the board. So hopefully that makes sense also. Yeah, I'm reading in the comments that can we do a base 3 algorithm? That's initially that's how I did it, but it was a bit complicated to explain, so I just used bits. But yeah, you can just deserialize your single field elements. You can represent it as a base 3 number and store your TicTacToe like that also. Okay, so once we updated the board, we need to serialize it back into the states. Serializing is exactly the reverse operation of deserializing. We recreate these two lists of 9 bits. And if this was not obvious until now, bits are represented as bools. True is 1 and false is 0. So there's really nothing magical here. I'm not going to spend too much time here. We just use field of bits, which is the reverse of field of the 2 bits function that we used previously, with the concatenation of these 2 lists that we recreated. And then we update the state. We saw that function before, the set function, to just update the board with the new board. And now, so that's the last function. It's a bit tedious to write or to look at, but there's really nothing crazy going on there. To check if we won, we set this one variable to false. And then we check every rows, columns, and diagonals. And if there is someone who won in any of these, one will be set to true via some OR logic. And then at the end, we set the game done to this one. So one may be false if nobody won. So it's a no up, basically. Or it will be true if anybody actually created a row or a column or a diagonal. And maybe you can go through one together. Let's check the diagonal because it's easier. Here we have this dag1, and we have a number of conditions, and they are all connected with this AND logical operator. So if all of them are true, then dag1 is true. And so if dag1 is true, 1 will be true. So what are we checking here? We're checking that the top left tile was played. The middle tile is played. The bottom right tile is played. So 0, 0, 1, 1, 2, 2. They're all played. And the tile 0, 0 is equal to the tile 1, 1. And the tile 1, 1 is equal to the tile 2, 2. So somebody has played in all these tiles, and it's the same player who has played throughout all these tiles. And this is where it comes handy to have this optional type, because we can just write isSum instead of saying 0 or 1 for value. But anyway. So I see a question about dynamic indexing. So basically, as we said, like two things are, or maybe three things are kind of specific to Snapps. You cannot write big if and else block logics. That's the first thing. The second thing is that your for loops cannot be dynamic. They have to be static. So here, that for loop is always going through 3 elements. So that's fine. And I guess the third specificity is that you cannot index into an array dynamically based on a value in the that can change. So you have to, if you have an array and you want to change something in that array based on something that you computed somewhere or that was passed as an argument to the method, you actually have to go through the entire array to update that. Hopefully that answers the question. Okay. So I don't want to take too much time from my other co-speakers. So let's end this. So basically, if you want to play with this code, you can get the Snap CLI. I don't think we talked about the Snap CLI previously. At least I don't remember. But it's a CLI that command line interface that allows you to create projects more easily with Snap. So if you install it, you can just write Snap example TicTacToe, and it'll create a project with the TicTacToe code, and you can play with it, extend it if you want, etc. And if you kind of disconnected or you want to get this explanation again, or you didn't understand anything I was saying, or you don't like my voice, basically go on this link here, and there's the exact same tutorial in written format. So hopefully maybe that makes more sense and that can be helpful. Okay, I'm going to leave that slide up just for a few seconds, but I think Brandon is after me, if I'm not mistaken. Brandon, if you want to come on stage.
Hello. Yes. I'm going to share my screen. Oh, you have to unshare your screen first. There we go. Hello, everyone. Okay. All right. So, hi, I'm Brandon. I'm going to talk about how we handle privacy in our games. So, well, privacy in Snapps, but illustrated through games as we're doing. So yeah, so like, what if we have some secret state in our game, in an interactive game? How do we deal with that? I want to show, I want to illustrate this through the Battleship game. So unlike the last few examples, I'm not going to show a full implementation. I'm just going to focus on the interesting, new information here. So Battleship. Okay. For those who aren't familiar, it's 2-player. So 2 players sit opposite each other in this board game version. Each player positions ships in this grid, this 10x10 grid. And then after the setup phase, each player takes turns guessing, shooting a missile, I guess, at a square in the grid. And if they get a hit, then, the other player gives you like a red peg. And if it's a miss, it's a white peg. And then the game is over when all the ships are destroyed. So if we think about modeling this game, in the beginning, in the setup phase, player 1 and player 2 needs to set up their boards, and they need to do so in a way that remains secret throughout the whole game, at least until the end. And then after that, the game proceeds similar to TicTacToe. Player 1 picks a spot, then player 2 picks a spot, we update the board, we check for collisions, and you'd want to store this in state in some way. And then the end game is when one player hits all the ships. Perhaps you could do a maximum number of moves. You can be creative here. Just to show this in a state machine, and to start to explain, or start to sort of gently expose some of the interesting bits with the secrecy. Let's take a look at how this game fits together. Yeah. So player one sets up their board. That's the first state. Then player two sets up their board and they make the first move. And then the player one has to process the last move before making the next move. And then player two processes that move and makes the next move, and then we're in a loop. And actually, it's important that each player processes the move before. Because the board state is secret, the snap can't tell you if you've hit a ship or not. We need the actual player who set up the board to be the one to process that information. So let's just focus on the setup side, because this is the unique bit. So if we think about that, like how do we keep secrets? There's actually a ton of ways to do this. And if you're a cryptographer, you probably know like 12 off the top of your head. I'm just going to show one that is the most simple and makes sense in this context, which is to use a commitment. So first we need to generate some randomness. There's a random static method on fields. You can say field.random. And this secret randomness should be kept secret and not shared, obviously. So then what we do is we hash the board. So let's just pretend we have some representation of the board. You could do something similar to Gregor's in Sudoku, or David in TicTacToe. And then if you use a circuit value, it'll have a two-fields method automatically, and we can call Poseidon hash with the randomness and the board state. And then what we do is we take this hash and we store it in the state, and this is our commitment to the board. So and then now that the state is in place, when a move is being made, so I'm going to jump to like hypothetical code, pseudocode around moves. Let's say we're storing the last move, and move takes as private inputs the secret randomness and my board and my next move, which we'll process at the end. And the first thing we do is we check, just like Gregor showed, we check that the board that we're passing in is the same board that we've committed to by redoing the hash and asserting that it equals to the hash that's in the state. And once we do that, we can proceed as normal and do our logic to play the game. So hopefully that's clear. I want to go over a few more game ideas. I guess now's a good time to kind of mention to speak more about the projects. There have been a couple of questions about that. I think if we represent potential projects on a spectrum from what can like O of One Labs in our office hours support you the most with, to what can we support you the least with, I would say like the most support we can give you is if you pick a game that's very similar or exactly like one of these examples that we talked about. I guess TicTacToe and Sudoku we've shown you the full implementation of, so make sure you're very creative if you want to build off of those. But if you pick a game like Connect 4 that's similar to TicTacToe, we can provide a bunch of support. If you're not really familiar with building user interfaces, maybe you want to avoid building the UI part, and you can just make the smart contract part. That's also totally okay. And then if you come up with more creative games, and as you move towards other things that aren't games and things like extending the library, These are things that are all great projects, but we can probably support less. So just keep that in mind. So so let me give you a few more ideas and just give you like some idea on how you could go about implementing them. Mastermind. Okay. So Mastermind is another game that has an interesting like secret information. Like one of the players keeps their information secret. So in this game, one player, if you look at this plastic board, it's the bit all the way at the bottom. One player picks the position and colors of 4 pegs, and then that happens in the beginning. And then for the rest of the game, a second player makes guesses. So you can see at the top, that first guess is yellow, yellow, blue, blue. And the player who picked their initial configuration, they say how many pieces are like either in that set of 4. So you can see there's one piece that is blue, and how many pieces are both the right color and in the right spot. And in that first guess, there's none. So this is the game. You can look it up on Wikipedia if you want to learn more. So Mastermind. The game starts. The player sets up the board secretly, and again, think how we did it in Battleship. Then player 2 makes a guess, and player 1 responds and processes that guess before handing back control over to the other player. And I would recommend only storing the last move. There is a way in Snapps to store and refer to like more history, and this is a concept called sequence events. But we don't have great support for this. We haven't documented it enough yet, so stay away from that. I would recommend. And then the game progresses, and at the end, if the player runs out of turns, then the first player who picked the position wins, or maybe the other player guesses correctly, and then they win. So that's Mastermind. Let's just quickly talk about checkers or droughts if you're British. So checkers. Checkers has a fixed board state, so it's similar to Sudoku, I suppose, or TicTacToe. You can use 2-bit masks again to represent the board. There's a trick where the diagonals are empty. Thanks, Matthew, for pointing that out. So you can compress space even further, or you can also encode the information using like ternary, or you can be more sophisticated, but bits will work. The game proceeds where each player moves these pieces on these diagonal squares. Sorry, I assumed people are familiar with this game. Forgive me, but it's quite popular. And there's one sort of rule in checkers where if you capture a piece, which you do so by jumping over it, you can actually take another turn if you have another capture available. So the way that you could represent this is you could have the smart contract allow the player to like claim that they have more of their turn to take before handing control over to the other player. And so then you can have that player like send 2 like move updates before the other player takes their turn. And then the game end state is kind of complicated actually. You could fix the number of moves. That's an easy way to do it. You could make a timeout on every move, and then you can assume that if a timeout happens, then there was no move possible. So whatever you want there. And if you want more of a challenge, you can implement the king me rule, I guess, in checkers, where if you make a piece get to the end, then it becomes a king piece, and it can move backwards. And then maybe you need extra bit masks. Maybe you need like a more fancy encoding of the board to support that. In some people play with the rule that you win automatically if the other player didn't capture when they were supposed to. So, feel free to play with that. Yeah, so like I said, you can pick a game. If you pick one of these examples, we'll be able to provide the most support. Battleship is probably harder than like Connect 4, which is like a TicTacToe variant. But we're very excited to see what you come up with. I've been looking not at the chat, so I hope people heard me. Yes. Cool. So yeah, I'm gonna hand it over to Jason now, and yeah, thank you.
Cool. I guess I'm unmuted here. Perfect. Let me screen share. And I'm going to share my entire desktop for this one. All right, so let's talk about next steps. To just emphasize, the project that we're thinking of can be any game. You can use one of the ones that we went through, or that Brandon just went through. Any of those are good, or anything that you would like to do. It's really, the exercise is obviously really about practicing writing the smart contract. So you can certainly write a UI portion like Gregory did too, but in the interest of time, definitely start with the smart contract and start there. As far as creating your own project, the place to start is the Snapps CLI. So if you have Node.js and npm installed, and you'll need Node.js 16, you can just run npm install g, the global flag, and snap-CLI. And then with one command, snap projects, and whatever name you want to give it, you can set up the project structure, which brings a lot of goodies to it, including that if you were to commit your code and say push to GitHub, you'll have continuous integration as well. But we're still working on improving the test, but it's going to be a neat way to get started pretty quickly. And then don't forget David's example. You can also create using snap example TicTacToe. And then there was a comment asking for the most simple hello world. If you create this project, a new project, snap projects, whatever, the index file created in there will contain this. So thanks to Martin for adding this recently. It's a very basic example that just stores a number in the state, and then it adds 2 to it. So that's probably a good place to take a look and start. Reminder, if you, the first place to get help and to share and interact with other people in the program is Snapps-developers. It is a private channel for now. So it's only bootcamp participants. And then after the bootcamp, it will become public. But for now, if you're not in this channel, and most people should already be added to it, but if you're not, go ahead and ping 01 Regina, just DM her on Discord, and she can add you to this channel. And then lastly, a reminder on the upcoming times. We have in office hours, 2 hours long on Friday, and all the office hours use the same Zoom link. And then there'll be a pair of devs there to help you with questions. So there's one 10 a.m. to 12 Pacific on Friday. There's also an evening time, 8 to 10 p.m. Saturday, again, 10 a.m. to 12 p.m. And then on Sunday, when you're done with the project, we'll have a project submission form. And please submit your project by 7 a.m. Pacific on Sunday. And we're going to go through this pretty quickly and pick out some to show and have people talk about. And we'll email the people who get the chance to speak, if you want to, hopefully, at 9 a.m. Pacific on Sunday. And then that same day, that same Sunday, we'll have the wrap-up session. So this weekend, 10 a.m. to 12 Pacific. And we'd love your feedback anytime throughout the program, like today or later on. If you can go to omanlabs.org, bootcamp/feedback. We'd love to hear any ways to potentially improve SnarkyJS and just about your experience with everything. And we will share the link again in Discord for the project submissions, so you know where to do that. So thanks for joining us today, and we're going to have an open QA right now.
I just want to add really quickly. So there's a lot of really cool ideas for projects in the chat outside of games, and I just want to emphasize that's great. Like, let your sky be the limit. Let the sky be the limit in terms of the project ideas that you come up with, because it seems like a lot of people who are already kind of familiar with this stuff have a lot of really great ideas.
Sounds good. All right. Brandon, David, Gregor, do you guys want to join me here? I'll just have screen sharing. Awesome.
Hey.
Yes. All right. Let's go through some questions. VRF it looks like Isaac responded. We do not yet have a VRF, which is a verifiable random function, which would of course be very useful for games like poker. But it is something that we're planning to add. So in this case, Brandon, do you have a suggestion of what they should do?
I just wanted to say, Mina, like in the circuit for Mina's blockchain extension, well, consensus, we do have VRF implemented. But yeah, not exposed. Randomness, you can use, like if you want a random seed, you should use like state on the blockchain. We actually didn't show how to do this in any of the content here. Believe one of the examples should show it, but you can use like the one of the hashes, or like you could hash together the state hash and a bunch of things to kind of get your random seed. I think we will in a future version of the API provide like a better, more clear randomness. Isaac, do you have something to add?
No, I was actually going to chime in on some of the other questions, if that's okay. So I saw one of the questions here. Can we get some more info on data store / off-chain storage, or is that not ready yet? So it's I guess the way to say this is the Merkle tree functionality in SnarkyJS is implemented. It is not quite, it's not implemented with kind of a data store like file system or IPFS or S3 or anything like that. I think if you're feeling brave and willing to kind of dive into that code and take a look at how the in-memory one is implemented, I think implementing one of those persistent ones would be a really great project, because obviously that would be that's kind of a key primitive in a lot of different applications. I want to just also mention about oracles. So someone asked about oracles. So we have we have a technology or project that we call ZK Oracles, which basically is a means for importing web data into Snarks by using HTTPS transcript verification, TLS transcript verification. So basically any, this is not exposed yet, but basically the idea will be any information that's available via like just a normal HTTPS API, like JSON endpoint or any kind of REST endpoint or whatever, or even just an actual just like user-facing web page if you want to scrape it, can be kind of imported into a SnarkyJS program. And then I also just wanted to say, right, so sorry, I just wanted to bring up this question. Can you review what is private and what is public in your examples, e.g. TicTacToe, sudoku? I think that would be a really great one if someone wants to talk about maybe sudoku, because that one's kind of more private. Or I don't know, David, what do you think?
Yeah. So in my example, the sudoku, the initial sudoku was supposed to be shared outside Mina, but it wasn't on the blockchain. So everyone should know the task. But the solutions were supposed to be not shared outside Mina, and they were private in the smart contract. So the only thing that was public is just the state that I showed. That was the sudoku hash and whether the sudoku was solved. That was the only things public on the blockchain. But of course, you have to transmit the task somehow.
Yeah, I think more generally, you can see any state in your snap as public and any argument of your methods as private.
Yeah.
So for the TicTacToe, like the coordinates, the public key of the player who's playing, the signature, all of these things were private. Not that it mattered, but they were.
And just one thing I want to add, one thing that really tripped me up when I was first starting to write snark circuits, anything that's private, if you want to sort of make a proof that is actually sound, you need to assert things about that data. If you just perform a computation but you don't assert anything, then you can kind of prove anything. I don't know if that makes sense, but the assertions are very important.
I'll go ahead and share a couple links in here. The first is to the Snap docs, and we'll be adding more to this over time. And then also, just so everybody has it, here's the link for the project submission. So the form to have hopefully filled out by or before Sunday at 7 a.m. Pacific. And this is also used to indicate interest for the to be considered for the Snapps Builders program as well.
I wanted to address this question. Again, to confirm we can use any JavaScript within smart contract. If so, that should allow to call external APIs, right? So the answer is yes, you can use whatever you want. So think of it as SnarkyJS is just a JavaScript library. It's not a new language, but this won't create proofs. So if you just call any function on, so we have these special types that are fields, and you won't be able to pass a field into some library function, some external library function. And
yeah,
if you do and it works, it won't create a proof. So.
Yeah, I'll just expand that because it also connects to something someone asked. I believe Augustin asked about an example about like asserting things. So yeah, like if you just called a JavaScript function for reading from disk, for example. So that's fine. That would load the data from the disk, but it wouldn't prove anything about the data. So like it would just be some new data with no nothing kind of tying it to anything else. So you need to basically then kind of constrain that appropriately. So like, for example, with the data store thing, inside of those functions is code from like fetching from right now an in-memory data store, but could be on disk or IP, on network data store. But then once you fetch that data, you need to somehow verify that against some state in the snap. And the basic way of doing that is to store like a Merkle root in the snap, and then to verify the external data using Merkle proofs. So I hope that gives some idea. I'll just answer this other question here. So there's a question about sequencing. Is it possible to apply two valid transactions proof in a different order if designed properly? So yeah, so if two transactions don't make conflicting updates to the state and don't have sort of conflicting requirements on the state before being applied, they can be both applied independently of each other. But if they're touching the same piece of state, then only one of them will be applied.
Yeah, that's actually a great question. I'll add to that. So we kind of skipped over that in the architecture section. So in Snapps, we call these preconditions, and you can have network preconditions or account-related preconditions. So for instance, if you wanted a snap to only execute at a certain block height or after a certain block height, you could use a precondition for that type of thing.
I just see one other, just one other question I see here. So Philip asks, are there some docs on what exactly the inputs for verification key that's put on chain are, or some info on how circuit compiling works? So this is a kind of a broad topic, so I'm not exactly sure what you're most interested in, but let me just say the basic way that it works is every one of those methods in a Snap, smart contract gets compiled down into a circuit, and then basically a kind of like a hash of all those circuits is posted to the chain. So that's what actually lives on the chain. That's the verification key. It's kind of like a hash of all those circuits. So you can hard code values in there, like if you have some logic or like some data that you want to be kind of hard coded in the contract, you can hard code it in there, and it will sort of be like committed to on chain. Yeah, I would say if you want to know more specifics, please come to office hours, and we can talk more about it.
All right, great. Does anybody on the stage want to add anything else before we wrap up? All right. Sounds good.
That's a wrap.
Thank you for coming, everyone. Just keep in mind, you can go to the Snapps developer channel on Discord or join us in office hours, and then we'll see everyone again on Sunday. And any office hours are optional too, by the way. So
yeah.
Great.
Well, thanks everyone. Thanks everyone who put this together, and thanks to the audience also for being such a good audience. So, okay. Bye, everyone.
Bye.